Now, once we choose a basis, we can define a unique dual basis, which is a basis for the dual space. So I said that the dual space is a vector space. I haven't demonstrated it, but just take it for granted now that it is a vector space, and therefore it can have a basis. And now there's a canonical choice, meaning a natural choice. And we call this the dual basis, right, for the dual space. And that dual basis is defined by whichever basis we choose for V. So once we fix a basis for V, there is a natural basis for the dual space, which we call the dual basis. And that's our, what we call canonical choice or natural choice for the basis. Now, how is it defined? Well, let V be a vector space with this basis. Then the dual basis, which is our unique canonical dual basis, we write like this. So we use similar notation, but rather than subscripts, we use superscripts. Now notice that there are also n of these corresponding to the n in this basis. So this is always the case. If there are n in here, there will always be n here. But rather than subscripts, we use superscripts. So these are now elements of our dual space, just like these are elements of our vector space V. V star itself is a vector space. And so any basis will be a subset of that vector space, meaning each one of these is actually itself an element of V star. It's a covector or linear functional. And it's defined as follows, that one of these, let's say the ith one, acting on one of these, let's say the jth one, is equal to delta ij. And this delta ij is what we call the Kronecker delta. So it means the following. If I is not equal to j, so let me write it like this. Delta ji is equal to, so there are two parts of it, 0 if I is not equal to j, and 1 if I equals j. So this is 0 except when I equals j. So what this is saying is that E1 is 1, but E1, E2, E1, E3, and so on and so forth up to E1, En are all 0. These are all 0. So this basis vector in the dual space, when it acts on and one of the basis vectors in the vector space V, will only be non-zero if when it acts on, so if this is the first one, will only be non-zero when it acts on the first one of these. For all others, it will spit out 0. Now, first of all, why does this make sense? Let's think about it. If each of these is an element of this, so let's take the ith one, it's in V star. So this itself is a linear functional or covector. That means it acts on vectors V in V and gives us a number. Right? Now, what are these? These are vectors in V. So we can ask, what is this for the jth one? So for the ith basis vector in the dual space, we can act, what do we get when we act on the jth basis vector in here? We can ask that question. And we define, there's the important thing, we define these basis vectors. This is our choice. We are going to define these by this action. So we define the ith one so that when we act on the jth basis vector in here, we get 0 if j is not I. But if j equals I, we get 1. That's how we define it. So we define the first one like this. E1 is 1, and E1, E2 is 0, etc. E1, E3 is 0. And then E2, E1 is 0, E2, E2 is 1, E2, E3 is 0, and so on. So we are defining it this way. That's our choice. Okay, so this might seem weird. So let's see why we do it this way and where it comes from. So let's say we have chosen this basis. So let's fix a basis. Remember, bases are not unique. So let's fix a basis. Let's say we've chosen this basis for V. Then we know that we can write any V like this as a linear combination of these basis vectors. So in other words, a sum like this, a coordinate times one of them plus another coordinate times the second one plus and so on. So to write this out in full, this is V1 E1 plus V2 E2 all the way up to plus Vn En. Now let's take any covector, so an element of this dual space, and let's see how it acts on this vector V that we just wrote down in terms of the basis that we have chosen. So phi acting on V is phi acting on this sum. So we've expanded V, we've written it in terms of this basis. We've chosen this basis. And again, this is just a convention that we use for the vectors. For the coordinates, we use superscripts. Now, we know that phi is linear. So phi of this, V1 plus V1 E1 plus V2 E2, let's say we only have two of them, would be V1, because that's just a number, times phi acting on E1, plus, again, this is just a number, V2, phi acting on E2, right? And we have n of these, so plus V3 inside here, E3, and so on and so forth up to plus Vn En. Oops, Vn En. So we just carry on with this all the way up to plus Vn phi acting on En. So that's how we get this thing here. The properties of linearity of these covectors, they have to be linear. Okay, and remember that this is just a real number. So the result of this must be a real number because phi is a linear function. It acts on vectors in V. These are vectors in V, the basis vectors. So this will give us a number. So we've got numbers times numbers and then a sum over these. So we will get just a number. Okay. Now let's define phi subscript I as these quantities here. The linear functional acting on the ith basis vector in V, the basis we've chosen. So this is nothing more than the action of phi on the ith basis vector in V that we have chosen. And I reiterate, this is just a number because we've got a linear functional acting on a vector in V. By definition, that gives us a number. Then necessarily, going back to this, phi V has this form. So the action of phi on a vector must have this form where we've got the coordinates of our vector V times the action of phi on the ith basis vector for v. So necessarily these linear functionals have the form sum over I of phi acting on EI, which I'm calling phi I, the sum of these times the coordinates of V, the ith coordinate of V. So ith coordinate of V, which is precisely V superscript I. So any linear functional covector, once we choose a basis for V, this basis, and then we force the dual basis by the condition of the Kronecker delta, all of our linear functionals acting on vectors will look like the sum of the action of the linear functional on a basis vector I times the ith coordinate of V, the vector that we're acting on. So let me now define a dual basis, E1 superscript to En, by the following, which is precisely what I wrote down earlier. Now, notice that each of these, I've already said this, is a map from one of the basis vectors, which is an element of V, to R, because delta Ji is either 0 or 1, so it's a real number, right? And so this is a valid covector. So how does this act on a vector V? So if we define it like this, how does it act on some general vector V? Well, general vector V has this form in terms of this basis, right? So it's an element of our dual space, is a covector, so it satisfies linearity. So we can take this inside, right? I illustrated why on the previous slide. It's exactly the same reason. We're just replacing phi with EI, which is an element of V star. So we can take this inside the sum here. These are just numbers. So we get the sum of these numbers times EI acting on EJ. Well, we have defined this action via this. We're forcing it. So this thing here, these entities here, we are forcing them to have these values. In other words, this sum is over J, right? So we're summing from J equals 1 to N, and these will all be 0 except when J equals I. For J taking on any other value, these will all be 0. But when J equals I, this becomes 1, and we get VI. So this becomes VI because J equals I. We get VI times 1, which is just VI. So what's happening here? The way that we have defined these dual vectors, these covectors, which will form our basis, is that the ith one simply picks out the ith coordinate of V. That's what it does. So this is how we're defining them. So by writing this down, what we're forcing is that the ith basis vector for our dual space is simply the linear functional that picks out the ith coordinate of the vector that it acts on. That's it. Now, why does this even make sense? Well, it makes sense because what is the ith coordinate? It's a number. So EI acting on a vector V gives us the ith coordinate of V, which is VI, which is a number, and therefore this is indeed a covector, right? Now, is it linear? Yes. EI acting on V plus U. What would that be? Well, what's V plus U according to our definition of vector addition? Sorry, not according to vector addition. Let me just erase this so that we clear some space. So we want to assure ourselves that this is linear. So EI, is it linear? Well, we defined a basis. So let's pick two vectors, U and V. So U equals the sum of UI, EI, right? From I equals 1 to n. And V equals the sum of VI, EI in the same basis. So U plus V, what will that be? U plus V in this basis is going to be the sum of UI plus VI, which are simply numbers, times the basis vectors EI, right? And the sum over I. All of these are sums over I. Okay, so we've defined EI when it acts on a vector V as simply the ith coordinate of V, VI. So what happens when we act on this vector here, which has coordinates UI plus VI? We're going to get EI, U plus V, is equal to UI plus VI. Well, what's this? If we acted on U, we would get UI. And if we acted on V alone, we would get VI. So this is precisely EI acting on U plus, that's this, and this is precisely EI acting on V. So we do get linearity. And then we can also show that this holds with multiplication by a scalar, multiplying a vector by a scalar. Okay, so we are forcing this definition. We are forcing the definition of the dual basis, these special class of covectors or linear functionals, to be such that when they act on a vector V, they simply pick out the ith coordinate. So every covector or linear functional now has this expansion. It's equal to the sum or linear combination of phi I times these basis vectors EI, where phi I is the action of our linear functional on basis vector EI in the vector space V. Meanwhile, we force this to be the case. What's EI? Let's remind ourselves. When we act on a vector, what this will do, so let's think the way that we've defined this. Let's act on a vector V with this. What will happen is we will get, so this is the sum, oops, that's not a good, that's not a good attempt at sum. We're going to get the sum of phi I EI acting on V, right? It's the whole thing acting on V, right? Which is equal to the sum of these numbers phi I times EI acting on V. So sum from I equals 1 up to n, which is the sum from I equals 1 to n of phi I VI, because EI V picks out the ith coordinate of V. So we get this. Let's go back. That's precisely what we have here. Okay. So as I say, this is forced. Once we choose a basis for V, we force this representation. So we're forcing our linear functional covector to be written in a particular form. That form is such that when we evaluate phi, our linear functional, on a vector V, so we actually perform this map on some vector V, it results in the sum from I equals 1 to n of the evaluation of EI by phi, so phi acting on EI, times the ith coordinate of VI, which is precisely this sum here. So we have forced this outcome by choosing the basis. Once we fix the basis for V, we choose our dual basis like this to force this outcome. So now we have, although I haven't actually stated it fully yet, but we actually now have coordinate forms for both the vector and our covector, because we have forced a basis for the dual space. For the vector, we've already defined this. But for the dual space, we've now forced a basis, and we've got coefficients in that basis, namely these. So we've written an arbitrary covector as a linear combination of these basis vectors, and they can all be written like this, with these coefficients. So we can actually now define the coordinate form of a linear functional or covector phi as the tuple of these numbers. And again, we put these square brackets around phi to indicate that we're talking about the coordinate form. So we have now a coordinate form for V, which is V1, V2, up to Vn, this tuple. But by convention, we would write this as a column, V1, V2, up to Vn. Now, by convention, the coordinate form of a covector, rather than writing it as a column or orienting it vertically, we orient it horizontally. So we write it as a horizontal tuple. The coordinate form for a vector we write as a vertical tuple. Now, I'm sure you're wondering, why on earth, what the hell? Well, I'm going to explain this soon, because it does seem a little bit crazy until you sort of understand, historically why this happened and why this notation persists, of why we write these things as rows and why we write vectors as columns, or horizontal lists of numbers and vertical lists of numbers, or tuples. So I'll explain this in a second. But before I get to that, let me go a bit more abstract again.